In this talk, I will explain our recent work on three fundamental concepts in the theory of pseudorandomness: distinguishing, predicting, and certifying. This is a joint work with Edward Pyne and Roei Tell. Concretely, we are interested in two basic tools: Yau's lemma transforming a distinguisher to a predictor of a pseudorandom distribution, and more generally the reconstruction paradigm, which we will explain later. We first recall Yau's lemma. For a distribution D supported over n-bit strings, there are two standard definitions of its pseudorandomness, namely unpredictability, indicating that there is no feasible algorithm predicting the S bit from the first I-1 bit with noticeable advantage, and indistinguishability, indicating that there is no feasible algorithm whose acceptance probabilities over the distribution D and over the uniform distribution are bounded away from zero. The adversary model is usually probabilistic algorithms or circuits. A predictor is clearly a distinguisher, as a uniform distribution is statistically unpredictable. Yau's lemma suggests that these two definitions are indeed equivalent. From any distinguisher of the distribution D, we can obtain a predictor of it. Another standard tool in the theory of pseudorandomness is the reconstruction paradigm. It is a standard approach to explicit construction from hard strings. Suppose that we have an input string f that is hard in some sense. We construct an object OF based on f using an efficient algorithm. To prove that OF satisfies the desired properties, we assume towards a contradiction that OF fails to have certain properties. We will use a reconstruction algorithm showing that f is easy from the failure of such property. Therefore, if the string f indeed satisfies proper hardness condition, the construction of OF must be correct. One of the most notable examples is Nisan-Wilderson's pseudorandom generator from hard truth tables. Suppose that we are given a function f that is hard on average against a circuit. We can construct a pseudorandom generator from it. The correctness is proved by a reconstruction argument. Suppose towards a contradiction that there is a distinguisher C of the Nisan-Wilderson PRG using f. By applying Yau's lemma, we can obtain a predictor of the same PRG. Subsequently, we can use the predictor and the combinatorial design in the PRG to construct a small circuit computing f on average, refuting the assumption that f is hard. Similar framework is also used in construction of extractors, expanders, and error-correcting codes. We should note that both steps in the reconstruction of Nisan-Wilderson PRG requires randomness. An interesting question is the complexity of the reconstruction algorithm. This is because the hardness assumption we need for the function f depends on two parts: the complexity of the distinguisher C of the PRG, which depends on the derivatization task we want to do, and secondly, the complexity of the reconstruction algorithm, which in the example of Nisan-Wilderson PRG include Yau's transformation from distinguishers to predictors and construction of the circuit D from the predictor and combinatorial design. Specifically, suppose that both steps of Nisan-Wilderson's reconstruction can be de-randomized, we will be able to obtain a certified derivatization algorithm defined by Pyne, Raz, and Jan. That is, given f and the circuit C, the deterministic algorithm either outputs the approximate acceptance probability of C or report a circuit computing f on average. We note that certified derivatization already implies a collapse of BPP to ZPP, as with the certified derivatization algorithm, we can randomly sample a function until the certified derivatization succeeded. This is a zero-error polytime algorithm since most functions are hard on average. Indeed, such derivatization has been shown possible in a less general setting. Recent work shows that the second step of Nisan-Wilderson reconstruction can actually be made deterministic. Moreover, the first step, namely Yau's transformation from distinguisher to predictors, can be made deterministic if the circuit C distinguisher is a read-once branching program. Using these results, we can show certified randomization in space-bounded setting and obtain BPL equals L from uniform hardness assumptions. A natural question is, therefore, whether we can extend these results to classes stronger than read-once branching programs. Specifically, we can ask the following two questions. Can we obtain deterministic transformation from distinguishers to predictors beyond read-once branching programs, such as for general circuits, possibly under assumptions? Secondly, if we can do that, what is the relative strength of derandomization, certified randomization, and distinguisher to predictor transformations? In this work, we will consider both questions. Let's first consider the first question, namely whether there exists a deterministic transformation from distinguishers to predictors beyond read-once branching programs. The distinguisher to predictor transformation, or D2P transformation, is formally introduced by Doron, Pyne, and Tell. Given a circuit C from some circuit classes C, we are required to output a list P1, P2 to Pm of candidate predictors such that for every distribution D, if C is an epsilon distinguisher of D, at least one of the Pi is a delta predictor of D, where usually we set delta to be epsilon over order of n. Before asking whether there is a deterministic D2P transformation, we should first ask a simpler question. Do we expect the search problem is total? Perhaps surprisingly, this is indeed not a trivial question. Jiatu's lemma provides a randomized transformation from distinguisher C to a list of candidate predictors P1 to Pm. However, since it is unclear how to verify the correctness, we cannot easily derandomize the transformation using standard techniques, even with non-uniformity. In this work, we show that the answer to the question and the first question discussed before are both positive. The problem is total, and we expect that a deterministic algorithm exists. Indeed, we further show that there is a deterministic algorithm for the search problem if and only if derandomization is possible, namely promise BPP is equal to promise P. Therefore, derandomizing Jiatu's lemma is exactly what we need for derandomizing probabilistic algorithms. The proof of the theorem is not hard, and we will try to explain both directions of the proof. We start by considering the easier direction. Suppose that we are given a circuit C and an epsilon distinguisher to delta predictor transformation of C that gives M candidate predictors P1 to Pm. Our goal is to estimate the acceptance probability of C up to an error epsilon in time Pauli n and M. Our algorithm will indeed find the distribution D such that for each predictor Pi, its advantage for predicting P is at most delta. By the correctness of the D2P transformation, since the distribution is unpredictable, it is also indistinguishable, and therefore we can estimate its acceptance probability by the acceptance probability of the circuit over the distribution D. Next, we will show how the distribution D will be constructed. We will use an idea from the work of Goldrack and Widgerson, construct the distribution column by column. Suppose that we have already obtained the first I-1 bits of the distribution D. Our goal is to find the vector of length L for the ith distribution of D. Indeed, for each predictor Pj that aims to predict the ith bit, we can, from the first I-1 bit of D that have already been obtained, calculate the prediction of Pj to the ith bit. Therefore, it suffices to construct a column against all predictors. We can then reduce the task to the following algorithmic problem. Given at most m vectors P1 to Pm of length L, we need to find a vector V that is far from each Pi in Hamming distance. It is folklore that a pairwise independent distribution samples a good V with nice probability when L is sufficiently large polynomial in M. This gives the following algorithm. we enumerate all sets of a pairwise independent distribution and find a good V, which runs in time polyam. Indeed, we use a stronger algorithmic tool in our paper to achieve better parameters. Next, we consider the other direction. Suppose that promise BPP equals to promise P. Given a circuit C of n inputs, we need to find a list of circuits P1 to Pm that is an epsilon distinguisher to epsilon over On predictor transformation for M is poly-M. Note that from the assumption that promise BPP equals to promise P, we can estimate the acceptance probability of a circuit up to an inverse polynomial additive arrow. We will construct P1 to Pm using a CAP algorithm with a sufficiently small inverse poly arrow. And indeed, we will derandomize the probabilistic D2P transformation from Yau's lemma. We will employ an idea that appears in an earlier work of Goldrack. Recall that Yau's lemma is proved as follows. Suppose that C is a distinguisher of the distribution D. Let X be sampled from D, colored in blue, and Y be sampled from the uniform distribution, colored in orange. By a hybrid argument, there is an I such that the gap between the acceptance probability of C on these two inputs is at least epsilon over n. For each I and each sigma 1, sigma 2, we define the function Piy sigma 1, sigma 2 as follows. We evaluate the circuit C on the concatenation of the first I minus 1 bit of X, sigma 1, and Y, and we output the XOR of the output of the circuit and sigma 2. Here, the 2 bits sigma 1, sigma 2 are used to deal with, for example, the absolute value, so for simplicity, let's just assume that both of them are 0. Similar to the proof of Yau's lemma, we can show that for some I and over a uniformly random Y, the probability that the predictor Piy fails is bounded away from 1/2. In other words, the expected value of the output of P and Xi is smaller than 1/2 minus epsilon over n. By swapping the expectation symbols, this further indicates that over a random X from D, the expectation of the difference between Xi and the acceptance probability of Piy over a random Y is smaller than 1/2 minus epsilon over n. Let's define tilde Pi be the function outputting the acceptance probability of Piy over a random Y. We can notice that tilde P is indeed a non-Boolean predictor, in the sense that it outputs a number between 0 and 1 that is close to Xi in expectation when X is sampled from the distribution D. Crucially, we can observe that the non-Boolean predictor tilde P can be approximated very well using a deterministic CAP algorithm, which follows from the assumption that promise BPP equals to promise P. After obtaining a non-Boolean predictor tilde Pi, we need to transform it into a Boolean predictor, namely a list of circuits P1 to Pm, such that if C is an epsilon distinguisher of D, one of Pi is an epsilon over On predictor of D. And the solution is to use the trick of discretization. Let B be a sufficiently large polynomial in N, we evenly divide the interval from 0 to 1 into B subintervals, each of which is of length 1 over B, which is the precision of the discretization. One can observe that the expected difference between the output of the non-Boolean predictor and Xi is roughly the same to that of the discretized predictor, where we first randomly sample a positive integer tau smaller or equal to b, and output 1 if and only if the output of the non-Boolean predictor falls into the first tau intervals. Concretely, let tilde pi tau be the Boolean output function that output 1 if and only if the output of the non-Boolean predictor falls into the first tau intervals. By an averaging argument, we know that there is a tau such that pi tau fails to predict the s bit of x with probability at most 1/2 minus epsilon over n plus a higher order term. In some sense, the idea is similar to the approximate calculation of the finite integral of a function. Subsequently, tilde pi tau for I from 1 to m and tau from 1 to b is a valid list of predictors for any distribution D that is distinguishable from uniformly random by the circuit C. This completes a proof as tilde pi tau can be implemented by a uniform deterministic algorithm given the circuit C, as by the definition of the non-Boolean predictor and its discretized version tilde pi tau, we only need to estimate the acceptance probability of Yau's predictor piy, which reduces to the circuit acceptance probability problem that is deterministically solvable under the assumption that promise BPP equals to promise P. Let's have a short summary of the proof. Suppose that we have a D2P transformation P1 to Pm using the algorithmic problem solvable by pairwise independent distribution. We can construct a candidate pseudo-random distribution column by column, which is unpredictable by any of the predictors. And given the correctness of the D2P transformation, we can assure that it is not distinguishable by C. Conversely, suppose that promise BPP equals to promise P, we can use the Yau's lemma to construct a non-Boolean predictor by implementing the Yau's predictor and calculate its acceptance probability. By discretization, we can obtain a list of Boolean predictor, which fulfill the construction of distinguisher to predictor transformations. We will also briefly mention the consequences of our results and techniques. Using the proof idea of theorem 1, we can actually construct unconditional D2P transformation beyond read-once branching programs. By constructing unconditional D2P transformation for certain graph problem as distinguisher, we can prove UL equals to NL from uniform assumptions. Moreover, for the same graph problem, we can design an unconditional catalytic log space algorithm using the idea of D2P transformation. We also have many other consequences, including the new proofs of classical results in the theory of derandomization, which can be found in the appendix of our paper. In the rest of the talk, we will consider another question posed before, which is what is the relative strength of derandomization, certified derandomization, and D2P transformation. Recall that D2P transformation is formally defined as a search problem, where for a given circuit C, we need to output a list of circuits P1 to Pm, such that for every distribution D, if C is a distinguisher of D, at least one of Pi is a predictor of D. In an earlier work of Pyne, Roei, and Zhang, they also define certified derandomization, where given a circuit C in some circuit classes C, and a function f that is supposed to be a hard function, we output one of the following two cases. Either we can derandomize C by output a number within 0, 1 that approximates the acceptance probability of C within an additive error of 1/3, or we output a small circuit C computing f, which effectively refutes that f is a hard truth table. In theorem 1, we have already proved that D2P is equivalent to promise BPP equals to promise P. It is straightforward to see that by simply ignoring the function f from promise BPP equals to promise P, we can get certified derandomization. Moreover, we can also do this using the derandomized Nissan-Widgerson introduced in the work of Pyne, Roei, and Zhang. Certified derandomization is also known to imply promise BPP equals to promise ZPP, as we mentioned before, using the technique of randomly choosing functions. So there are two concrete questions. Is D2P necessary for certified derandomization, or it is an overkill? Secondly, is certified derandomization necessary for promise BPP equals to promise ZPP, or is it an overkill? We answer the question by showing a complexity theoretic characterization of certified derandomization. We show that certified derandomization is equivalent to promise BPP equals to promise lossy, where promise lossy is a set of promise problems reducible to the lossy code problem introduced by Cotton. Namely, suppose you are given a pair of circuits representing a compression-decompression scheme. Your goal is to find a string that is incompressible by the scheme. We note that promise P, promise lossy code, promise ZPP, promise PPP are contained in this chain, but it is not known to collapse. For the first question, we can see that D2P is probably an overkill for certified generalization, unless promise BPP equals to promise P can be implied by the weaker collapse promise BPP equals to promise lossy. Moreover, certified generalization may also be an overkill for promise BPP equals to promise ZPP, unless promise BPP equals to promise lossy can be implied by the weaker collapse promise BPP equals to promise ZPP. Let's have a short summary of our result. Firstly, we obtain the equivalence between deterministic D2P and promise BPP equals to promise P. Namely, Yau's lemma is exactly what you need when you want to derandomize promise BPP. Using the proof idea, we unconditionally construct distinguished to predictor transformation beyond read-once branching programs and obtain applications in some hard problems such as UL versus NL. Secondly, we characterize certified generalization and D2P using the collapse of promise BPP to promise P, promise ZPP, or promise lossy, which classify the relative strengths of generalization, certified generalization, and D2P transformation. There are many open problems left in our work. Are there more examples of unconditional D2P transformations for distinguishers beyond read-once branching programs? Are there any other consequences from the proof of the equivalence between D2P and generalization? For example, we have already had consequence in UL versus NL. What are other consequences? Also, we call for further study of certified generalization and the class promise lossy, as it will probably improve our understanding to the reconstruction paradigm in the theory of generalization. That's all for today's talk, and thanks for listening.